Hi, my name's Dr. Colin Campbell. I'm a senior research scientist here at Meter Group, and today we're going to be talking about water content. Now, the focus here today is to discuss this at a level that'll just give you a little taste about water content, why we measure it, and some of the challenges associated with it. If you want to know more, head over to metergroup.com. There you'll be able to dig into our knowledge base and learn quite a bit more about the subject. So without further ado, let's start talking about water content. Now, one of the first questions people ask me is why measure water content? Well, in general, it's one of the easiest measures to make in the soil, and we've been making it for a lot of years. So it's not hard to understand why people would want to do it over and over. If you're trying to understand how much water is available to the plant, though, you better go over and watch our water potential video because you'll need to know more about that. Measuring water content helps us with water balance. It helps us to know how much water is going into the soil, helps us in a large system to understand what might be going out and what might be running off. So today we're going to talk about some ways to measure it and some things you need to know before you get started on your water content journey. There are two types of water content, gravimetric and volumetric. They're similar, but you need to understand that they are different in certain ways. Gravimetric water content really is the one that you've heard of. It's the one where you just go out in the field, you take a soil sample, bring it back in the lab, you weigh it on a scale, you dry it in the oven, and you weigh it again. And gravimetric water content, W, is just equal to the mass of the water divided by the mass of the soil. It's pretty simple, and a lot of grade school kids do this in little activities they do. For you, though, I'm guessing you want to know more about water content because you're wanting to measure it in the field. And in the field, we don't measure gravimetric water content. At least it's pretty difficult to do so. Most measurements done in the field are volumetric water content. So let's talk a little bit about what that is. So if we had some way to separate the soil, the water, and the air out of a soil sample where it's all mixed together, we could describe this volumetric water content, theta, as the volume of water divided by the total volume of the sample. So it's a little bit different than the gravimetric water content where you're dividing by the mass of soil. Now, the volumetric water content, as I said, is something we use out in the field. But first we got to understand what are the ways we can measure it out there. So let's talk about that. There are several ways to measure volumetric water content in the field, and I want to make you familiar with each one of these. First, let's talk briefly about measurements with satellites. Now, this is what we call remote sensing. And when we measure water content in this way, we're only really getting about 5 centimeters of the upper surface of the soil. We're also doing it in a fairly large footprint, hundreds to thousands of meters on each side. So these pixels are large. But if you want to try to understand the water content of larger areas, this is exactly what you need. And a lot of these global models use this approach. Now, a mid-range measurement of volumetric water content is done by a neutron measurement system or maybe a gamma measurement system. These use naturally occurring gamma or neutrons, and they actually connect that to the amount of water in the soil. Now, I could teach a lot more on that. We don't have time, but essentially we measure those counts and we turn it into a measurement of volumetric water content. The distance you can get out of these is, say, something like 50 meters in diameter all the way up to somewhere 500 meters in diameter or above. So these, depending on the system of measurement, you can get quite a large footprint. And one of the nice things is you can connect them to the satellite measured data. One of the challenges with these systems is the depth that they measure. For example, a neutron system sometimes measures around 20 centimeters deep in the soil if the soil is wet, but can extend all the way down to 70 centimeters deep if it's dry. A gamma system maybe can only read 5 to 10 centimeters in the soil. So they have their limitations. The good side, you don't have to dig soil pits. You don't have to dig installation holes. The bad side, the accuracy may not live up to quite your expectation. Now, I'm guessing if you're watching this, you're wanting to know a little bit more about in-situ sensors. So let's talk about that. In-situ sensors means we have to dig some kind of hole down in the soil, and ideally we stick our sensors into undisturbed soil and we leave them there. And we monitor them with a data logging system above the surface, and we watch the water content over time. It takes quite a bit more effort to install these, and we'll talk about ways to lessen that effort, but the overall results are quite good. Usually you don't see the scatter in these data that you might experience in the satellite or a Neutron/Gamma system.